Tell me when to start.
Yeah, tell you. So now the meeting is streaming live on YouTube. So
okay.
Welcome everyone. Good morning and Happy New Year. I take this opportunity to send my best wishes to all the audience and welcome to the new season of the QISS virtual seminar. So today we will start with Richard Healey, and in the coming weeks we will also have Lise Moline, Stephen Wolfram, Doreen Fraser, Laurent Fredel, Alex Kissingers, and others that will be announced later. So today we are listening to Professor Healey from the University of Arizona, and is going to talk about whether facts are relatives or not. So this conference is recorded, and there will be time for questions after the talk. So Richard, it's your turn.
Thank you. It's a privilege and a pleasure to be talking to you today. Before starting my talk, I thought I'd have a very brief introduction as to how it fits in with my current research. For a number of years now, I've been developing a unitary one-world view of quantum theory, which takes a quantum state not to describe the condition of a system to which it is assigned, but to have the primary function of yielding probabilities concerning what might happen to that system in future, concerning events, including measurement events in which it may become involved. And those probabilities are useful to any agent who happened to be in a physical situation that blocked further information about the events. For example, those events may lie outside the light cone of that situation. So the probabilities that the quantum state yields, which I take to be objective, unlike cubists, are tailored, as it were, to specific physical situations. And changing the physical situation changes the probabilities. The probabilities are therefore relative to physical situations, and the quantum state which generates them also is relative. So a system doesn't have a quantum state, but relative to different physical situations, it may be assigned a quantum state. Okay, so the probabilities, the quantum state, are relative, but to a first approximation, the events which the quantum state gives you probabilities of are not relative, but absolute. But you can think of today's talk as probing the limits of that approximation. So here's an introduction. In order to get through this talk, I'm going to read quite a lot because I want to get everything out to you. And the most interesting part of the talk is at the end. So there might be all kinds of technical questions you want to ask me in the part of the talk, but I strongly recommend that you don't grind the talk to a halt because the interesting stuff comes towards the end. So a number of physicists, including Časlav, have recently described scenarios that extend the scenario of the Gedankenexperiment of Wigner's friends to argue that the application of unitary quantum theory here conflicts with the assumption that a quantum measurement always has a unique objective outcome. And some people have concluded that the outcome of a quantum measurement is not an objective, but a merely relative fact. As I was saying before the discussion started today, you can resist that conclusion by raising objections to each individual argument, and I've done a fair amount of that. Not because I wanted to disagree with the conclusion. I thought the conclusion was probably true, but because I was not convinced by the details of the arguments which had been put forward to establish that conclusion. But I'm not going to take that line today. An alternative response, which I am going to pursue today, is to analyze the content of the conclusion, to see exactly what it implies for the objectivity of science, which as a philosopher of science, I take to be a very important desideratum. So what I'm going to do is sketch one of the two cleanest existing arguments in this genre. By cleanest, I mean it relies on the fewest and least controversial assumptions. Then I will argue that no quantum measurement outcome will ever lack the kind of objectivity that matters for science. Okay. So here are some of the papers that I'll be, well, here are some kind of juicy quotes from what people said this summer in August. First one from Czaslaw, facts are relative. A commentary on a paper, first author Bong, theoretical work done by Eric Cavalcanti and Howard Wiseman and one other fellow whose name I forget. Eric Cavalcanti comments at the bottom in the conversation piece. If a tree falls in a forest and no one is there to hear it, does it make a sound? Perhaps not, some say. And if someone is there to hear it, if you think that means it obviously did make a sound, you might need to revise that opinion. The middle quote is from George Musser, writing in Science magazine. Paradox puts objectivity on shaky footing. Quantum test of venerable thought experiment suggests facts are relative. So this is sort of obviously of interest to a philosopher like myself. Here are some of the papers where these things come out. The Bong paper is the first one here, on which Czaslaw was commenting in this third paper. Czaslaw himself had an earlier sort of ancestor of the Bong paper, if you like. Cavalcanti's quote comes from here. I mentioned also the Frasche and Renner paper earlier in the same genre. This is my paper from Foundations of Physics, critiquing two earlier arguments, that this one by Czaslaw and this one by Frasche and Renner, but putting forward a third argument, which I was convinced by. This paper here is on the archive, and basically what I'm going to tell you today is contained in this archive talk. The particular argument I'm going to use today, and did use in this paper on the archive, is due to a young philosopher, Gees Leegwater, in the Netherlands, entitled When Greenberg, Horn, and Zeilinger Meet Wigner's Friend. So I'm going to develop Leegwater's argument, and as from its title, you can guess it's going to have to do something to do with Wigner's friend and something to do with the Greenberger, Horn, and Zeilinger thought experiment and real experiment. So I'll go through it in those three stages. First, Wigner's friend, second, GHZ, and third, putting the two together. So first stage, you're all familiar with, so I'll go through this quite quickly. I shamelessly stole one of Czaslaw's slides here because he can draw things where students can, and I can't. Okay. Wigner's friend performs an ideal von Neumann measurement of the z-spin of a spin-half atom assigned a superposed x-spin up state. And this would perfectly correlate an initial z-spin eigenstate with a corresponding final state of the lab, where up is the state of the entire lab correlated with a z-spin up eigenstate, and down similarly correlated with z-spin down eigenstate. But of course, this measurement is actually performed on an x-spin up eigenstate. So we end up with an entangled superposition. And if we believe unitary quantum theory, which is a given for this talk. And Wigner can observe his friend's outcome by measuring GZ. And if he gets GZ equals +1 for this measurement, that apparently at least confirms the outcome was up, and GZ equals -1 apparently confirms that it was down. But he can instead choose to measure a different observable, JX, on his friend's entire lab. Of course, this is a very difficult measurement, and that'll be important later in the talk. But consistent with unitary quantum theory, this is possible, in some sense of possible. And if the contents of the lab after his friend's measurement are represented by the unitarily evolved state, which I've been assuming, then Wigner will certainly get JX equals +1, But if there's been some physical collapse interior to the friend's lab, he's equally likely to get the outcome Gx equals -1. And after several repetitions, it would be extremely unlikely, if there had been a collapse, for him to get Gx equals +1 every single time. Okay, so much for Wigner's friend. What about GHC? Well, consider 3 spin-half atoms, A, B, and C, and prepared in the GHZ state, which is basically a superposition of 2 components, the first of which has each of these atoms in a +1 Y spin state, and the second component has each of the 3 atoms in a -1 Y product state. And we have a superposition of the 2, and for technical reasons, we have a factor of -I in there. Okay. So what do we know? The spin component of each atom is certain to be measured as ±1. More interestingly, the product of the 3 X spins is certain to be measured as -1. And if the X spin of one atom is measured along with the Z spin of the other 2, the product of the 3 results is certain to be +1. So for purposes of contradiction, assume that the outcome of a spin measurement on each atom is predetermined independently of what's measured on the other atoms. So then let A, B, and C equal the predetermined values for the X direction, and U, V, W be the predetermined values for the Z direction, for the atoms A, B, C respectively. Then we get, as a prediction of quantum theory, that A times B times C equals -1, and A times B times W is +1. Okay, so if you consider equations 4 through 6, the last 3 of those 4 equations, multiply them all together, you get A U squared, B V squared, C W squared. U, V, W is squared, so whether they're + or -1 as predetermined values, the square is always +1. So multiplying those equations together, you get A times B times C equals +1, which contradicts equation 3. A times B times 3 is -1. So we have a paradox, and the usual way of resolving the paradox is to simply deny that there were predetermined values for the X direction and predetermined values for the Z direction. Measurement creates the value; it simply doesn't simply show you what was already there to be found. So far, we don't have any paradox, but now we put the 2 together, Wigner's friend and GHC. Now we can get a paradox, which is going to be what I reflect on for the rest of the talk. So what we do now, we have 3 experimenters, Alice, Bob, and Charlie, each of them confined to a physically isolated laboratory, to perform just one measurement of Z spin component on a single spin half atom. There's no repetition of measurements. Statistics are essentially irrelevant to this argument. And we assume that those 3 atoms are assigned the GHZ state that I just showed you. We assume the 3 measurements are space-like separated and simultaneous in the lab frame sigma, and that the measurements are all ideal von Neumann measurements. This is a thought experiment, remember. You'd never be able to do it in the lab, but that doesn't matter for the logic of the argument. Each experimenter has a friend who subsequently measures an observable on their lab, analogous to the observable Jx in the original Wigner's friend scenario. So we have 3 friends. Eugene measures this observable, which I'll call XA, on Alice's lab. Johnny measures the analogous observable XB on Bob's lab. And Daniel measures the analogous observable on Charlie's lab. And those friends' measurements are again assumed to be all space-like separated and simultaneous in the same lab frame sigma. Okay, now we're going to start looking at space-time relations amongst all of these 6 measurements. And I'm going to give you a picture, but before giving you the picture, a space-time picture, I want to give you some information to help you to interpret it. Overall, the diagram illustrates the space-time relations amongst all 6 measurements. Colored triangular planes mark simultaneity slices. They're blue in the lab frame sigma, in which Bob's and Charlie's outcomes occur simultaneously with Alice's, and purple in a different frame, sigma primed, in which Bob's and Charlie's outcomes occur simultaneously not with Alice's, but with Eugene's. There are two further frames necessary for the argument, which are not in the picture because it would just be a big mess. But showing you these two frames gives you the general idea. So here we have it, right? The unprimed T's indicate simultaneity slices in the sigma frame, and the primed T's indicate simultaneity slices in the sigma prime frame. So you can see Alice, the sort of broad colored vertical lines indicate the duration of the relevant measurement. So you can see the space-time separations by looking at the diagram. So between T0 and T1, Alice, Bob, and Charlie make their measurements on their spin-half patterns. And between T1 and T2, Eugene, Johnny, and Daniel make their measurements on the entire labs of Alice, of Bob, and of Charlie, respectively. But you see, at T1 primed, the measurements of, at T1 primed, Eugene, Bob, and Charlie are just about in the primed frame to make their measurements. And by a later time, T2 primed, they have all finished their measurements. But remember, in the primed frame, Eugene's measurement was simultaneous with Bob's and Charlie's. Okay. There will be other frames in which Johnny's measurement is simultaneous with Alice and Charlie's, and in which Daniel's measurement is simultaneous with Alice and Bob's. If I got the things right, I think I did this time. Okay. So that's the setup. And remember, well, I'll just continue with the argument. Okay. This presents a paradoxical scenario in which the application of unitary quantum theory assigns probability 1 to an inconsistent set of statements about 6 actual measurement outcomes. All of these outcomes are assumed to be actual, and there's no repetition. The argument for this conclusion rests on these two key assumptions. One I'll call universality of quantum theory. Unitary quantum theory with the Born rule applies to every isolated system in any frame, including to the contents of an isolated laboratory in which a quantum measurement is performed. And another assumption, which I'll call single outcomes, any quantum measurement has a single outcome, which is independent of the frame in which the outcome is described. Now, I believe that that's essentially all you need to derive the paradoxical conclusion. You don't need to assume locality. You don't need to assume something like no superdeterminism, in the words of the Bond paper, because no choices are involved. These are specific measurements which are assumed to be performed and to have the single outcomes that they do. Okay, so I'll show you in a minute how this contradiction emerges, but to be quite precise about what the contradiction is. Single outcomes alone implies that exactly one of the following sentences is true while the other is false. A, the outcome of Alice's z-spin measurement at T1 is spin up. A primed, the outcome of Alice's z-spin measurement at T1 is spin down. You have similar pairs, similar contrary pairs for describing the outcome of Bob's measurement and the outcome of Charlie's measurement. When it comes to the friends, Eugene can use one of U or U prime to truly state the unique outcome of his XA measurement. And you can see on the slide what these sentences state. And there are analogous sentences for Johnny and Daniel concerning the outcome of their measurements on their, the labs of their friends, Bob and Charlie. So single outcomes all by itself implies that exactly one of the sentences of the form S, and there are 64 of them, truly states that all 6 measurements have these particular outcomes. Okay. We haven't yet used quantum theory. We've just said what single outcomes commits one to. But analogous to the GHC condition, we can apply quantum theory to show that with probability 1, according to the Born rule, the product of the outcome results of Eugene, Johnny, and Daniel is -1, and the other products of the outcome results of Eugene, Bob, and Charlie +1, Alice, whoever that was, I've forgotten, is +1. Multiply the second, third, and fourth together, and you get +1, which contradicts the first equation, which says U times V W equals -1. So there's no assignment of a value of plus or -1 to each of U, V, W, A, B, C consistent with those equations 7 through 10 above, which means there's no truth value assignment to all of those sentences I gave you on the previous slide consistent with those equations. Every single sentence of the form S, and there were 64 of them, implies a set of values that violates at least one of those equations 7 through 10. So we get our paradoxical conclusion. Universality of quantum theory implies the probability 1 that single outcomes is false. And again, we didn't have to assume repetition of measurements. We didn't have to assume locality. We didn't have to assume no superdeterminism. We don't quite have a logical contradiction because all quantum theory tells us is that with probability 1, single outcomes is false. Probability 1 isn't impossibility, at least for me as a philosopher. Okay, so what to do about this? Well, one way of getting rid of a contradiction is well known to philosophers, and that's to say, a sentence doesn't always make the same statement when it's uttered in different contexts. So if I tell you it's 5 p.m. and you tell me it's 8 p.m., it looks like that's a flat out contradiction. But if one is made in Tucson and the other is made in Manila at the same moment, then there's no contradiction. So maybe you could get rid of the paradox by appealing to what I call use contextuality. The different contexts in which sentences like A are used by Ellis and the other experimenters to state the outcomes of their experiments. I'll warn you ahead of time, this doesn't work, but let's try it anyway. Okay. To evaluate the truth of a sentence, including a term like here or now or I or you, ways used in context, you have to specify the reference of that term. Philosophers call these things indexicals. The sentence it is 5 p.m. is use contextual because the word is in the present tense functions as an implicit index. Is now. So you put the now back in, which is merely implicit in the present tense. So is there any reason to think that a sentence like A is use contextual? Here's A again. The outcome of Alice's Z-spin measurement at T1 is spin up. Well, it doesn't matter who says that because we've already got Alice named as, if you like, the speaker. It doesn't matter where that is said because obviously this pertains to something that happens in Alice's lab. It doesn't matter when it's said because the time is already plugged into the sentence A. This is not a contextual sentence like it is 5 p.m. We've already explicitly said at T1. So as far as I can see, there are no grounds for thinking that the truth value of A is dependent on the context in which that sentence is used. So the paradox remains. But I think it's too early to give up on contextuality altogether. We have to be a bit cleverer here. And philosophers have considered another kind of contextuality, not use contextuality, but what John McFarlane calls assessment contextuality. John McFarlane is a philosopher of language, amongst other things, at UC Berkeley. And he's extended another philosopher, David Kaplan's seminal work on semantic contextuality to defend what he calls analytic truth relativism. So what's the basic idea of analytic truth relativism? The idea is that assessment of the truth of a sentence may require not only a specification of its context of use, but also its context of assessment. I mean, forget who, when, and where the statement was used. Just look at its content. Its content still may depend on the context in which it's assessed. So McFarlane gives us the example. Licorice tastes good. Well, some people think it does, and some people think it tastes disgusting. That sentence can be assessed as true in the context of Alice's states. She liked licorice, but false in the context of Bob's taste. So if you're an analytic relativist, then there is no absolute fact about whether licorice tastes good. They're just a relative fact that it tastes good when true. Sorry, that the sentence licorice tastes good is true when assessed in contexts like Alice's, but false when assessed in contexts like Bob's. Now, Časlav and other people talk of relative facts when discussing extended Wigner's friend paradoxes. So I asked myself, is this a case of analytic truth relativism? The thought there being that contextuality matters, but it's not the context in which a sentence is used that matters, it's a context in which it's assessed that matters. Well, I asked you a question, is this a case of analytic truth relativism? And my answer is no. Whoops. It's not, but we're getting closer to a way of resolving the paradox here. We can still use this idea of assessment contextuality to resolve the paradox, but this requires three things. First of all, we have to come clean and say what counts as a context. Secondly, we have to state conditions under which the truth value of a sentence is accessible at all in a context. And thirdly, we have to actually say what's involved in assessing the truth value of each of the sentences we're concerned with in the paradox A through U, which is accessible in that context. So I'm going to go through this now to show how this works. First question, what is an assessment context? Well, you might think that an isolated laboratory is what we should call an assessment context. But actually, that's not quite right, because an isolated laboratory at one time provides a different context from the same isolated laboratory at a different time, when the outcome has become apparent in that laboratory, for example. So I'm going to say a quantum measurement has an outcome when a measurement takes on, when a magnitude takes on a value. A detector produces a current, points to a marker on a scale, another kind of detector just clicks, whatever. And I'm going to say that a magnitude takes on a value following a suitable interaction in a space-time region, which can be modeled by quantum decoherence in that region. So now I'll tell you what an assessment context is. An M decoherence environment E of a quantum event E, in which a magnitude M takes on a value, is a region of space-time Re that includes the region where the event occurs, together with physical processes in that region that can be modeled by robust decoherence of a system's state in a pointer basis associated with different values of M. So that's the kind of context in which we're looking to assess the truth value of sentences. So when is a sentence accessible? Well, a sentence about the outcome of a quantum measurement can be assessed for truth value only at an M decoherence environment for a magnitude whose value indicates an outcome. If you're not in the right environment, you can't assess a claim for truth value. A sentence about the outcome of a quantum measurement of magnitude N can't be assessed at an M decoherence environment if M and M are incompatible magnitudes. And also, a sentence about the outcome of a quantum measurement can't be assessed at a region of spacetime outside the region of any M decoherence environment E. Now, in my view, quantum theory can't explain, since its application simply assumes that a magnitude takes on one value rather than another in an M decoherence environment. Finally, assessment in context is up to us. Be in that environment and look, if you like. Okay. Now, what this means is that there are going to be limits on assessment. There are going to be certain situations in which these sentences A through U simply can't be assessed for truth value. It's not that they're false in some and true in others. There are some contexts in which they're neither true nor false, because they simply can't be assessed. But we need to understand how that can be. This is where I get interested as a philosopher. How can it be that there are limits to the assessment of sentences like this? And if there are limits, then isn't that going to place a really unjustified burden on scientific objectivity? And the way I see it, this is not an epistemic problem. It's not a problem about how you find out whether a sentence is true. It's deeper. It's a semantic problem. It means, what does it even mean to say that a sentence is true in that context? And only a verificationist would conflate these kinds of problems, the epistemic problem, the semantic problem. So I tried to think of cases in which we had a similar sort of problem. And one I actually found in Wittgenstein's philosophical investigations. I transformed it a bit for my purposes. But consider the sentence, "It is 5 o'clock here." Well, suppose, maybe it's hard to suppose somebody used that sentence on the sun. Would it be true right here and now? Well, there are problems in assessing its truth value in a context on Earth, because the sun is in no terrestrial time zone. There can't be any terrestrial clocks on the sun. An assessment of that sentence at a terrestrial time and place seems to presuppose a non-relativistic notion of absolute simultaneity. But if you think harder, our physics actually does provide a theoretical framework that can be applied to render that sentence accessible here and now on Earth. You have to place the sun, perhaps arbitrarily, in some terrestrial time zone. I think NASA puts the International Space Agency in GMT. And you have to simply specify which notion of distance simultaneity you're going to apply here, which frame you're going to pick in special relativity. And then you're going to allow that there might be very non-terrestrial clocks on the sun, frequency of atomic transitions, whatever. Once you've done all that, I think you are in shape, given our physics, to assess the truth value of H as used on the sun, assessed here at a time and place on Earth. I think you can do it. So physics is a success here. It tells you how to assess something in a context, even though at first sight it looks like it's going to be hard to do. But things could be worse. Think about the Gödel universe. Kurt Gödel, apart from being a brilliant logician, came up with a new model of Einstein's field equations, including a cosmological constant, in which there are closed time-like curves. Indeed, every point in Gödel space-time is connected to every other point by a closed time-like curve. It's as bad as you could imagine. So, pretend for a moment we're living in the Gödel universe, and somebody says, "It is 5 o'clock here." If they're not located right where you are, there's just no way you can assess the truth value of what they said, because there's no way of placing their utterance at some time relative to your present. There's no unique way of foliating. There's no way of foliating, to get no unique, the Gödel universe into slices of cosmic time, constant cosmic time. So the moral here is, look, there are cases in which physics can help you to assess things in a context where it might seem at first difficult. But there are also cases in which physics says, no, you just can't. That's simply not accessible in that context. So that's what's happening, I think, in quantum theory. If we take it that quantum theory is our most fundamental theory, then it's what tells us when you can assess a sentence for truth or falsity. How does it do that? Well, it's a probabilistic theory. It's applied by applying the Born rule, but the Born rule yields probabilities only for compatible sets of magnitudes. That means that you can apply quantum theory in an environment that is an MI decoherence environment for a set of compatible magnitudes MI, but that there aren't any MI decoherence environments or incompatible sets of observables. So quantum theory actually restricts the context of assessment to MI decoherence environments for each of a set of compatible magnitudes. That's why quantum theory is telling you there are certain contexts in which you simply can't assess claims about events, in particular measurement outcomes, for truth value. But again, I'm going to get more philosophical on you now, right? This is worrying, right? When Alice utters A after measuring her particle Z spin, she thereby takes herself to make a true statement, to state a fact. But if that statement is accessible as true only in certain contexts, then the objectivity of this fact comes into question. And so does the universal applicability of the notion of truth itself. But how could that be? How could a fact fail to be objective? How could the notion of truth have limited applicability? I mean, it's either a fact or it isn't. It's true or it's not true, you'd think. But actually, there's a prior question. What's the point of the notion of truth in the first place? Why do we have that notion? Why do we need it? And why do we even talk about facts or statements of fact? Well, the philosopher Hugh Price has offered an answer in his 1988 book, Facts and the Function of Truth, and more recently in other papers. So there's a kind of philosopher who's called a deflationist about truth. He says, no, truth is not correspondence. No, it's not coherence. No, it's not sort of what works. None of those things. It has a very simple and humble role. Consider Donald Trump. He says a lot of stuff. He says he won the election. He says that the votes in Georgia were rigged. Now, if you disagree with him, you can say, well, Donald Trump says he won the election, but Donald Trump did not win the election. I disagreed with him without using the notion of truth. But he says so many things that it gets really tedious saying, Donald Trump said P and not P. Donald Trump said Q and not Q. It's much simpler just to say nothing that Donald Trump says is true. Now you've used the word true. You've used it, you've given it a role. It makes life simpler for you to use this concept. That's why we have a concept of truth on the deflationist view of truth. Well, Price is not willing to be such a radical deflationist. He thinks that truth has another role to play, the more socially significant role of spurring reasoned debate and so favorably aligning people's mental states. I came across an interesting article, opinion piece in the New York Times by Thomas Friedman. And he says, for example, without truth, there is no agreed upon path forward. The truth binds you. Okay, I'll leave it at that for quoting him. There's more in the opinion piece. Okay, so this is Price's idea. If we can all get on the same page, then we can achieve more together. The notion of truth is what we take as a norm and debating to try to get on the same page. More precisely, we get these benefits when our mental states are aligned. Which mental states? Well, the class of mental states have this, what he calls the same boat property, if their typical behavioral consequences are such that their behavioral appropriateness or utility is predominantly similar across a speech community. You know, we all agree, for example, that water is an important thing if you want to live. If a mental state has the SBP, then if it's appropriate for any one of us, it's appropriate for all of us. We're all in the same boat. Okay. Now, for my purposes, I need to generalize this principle or the property beyond a single speech community. So my generalized same boat property is this. A class of mental states have the GSBP if their typical behavioral consequences are such that their behavioral appropriateness or utility is predominantly similar across a collection of agents. They don't have to be in the same speech community. So then if a mental state has this property, then if it's appropriate for any agent in the collection, it's appropriate for all. They're all in the same boat. Okay. So consider a collection of agents. They're partitioned into speech communities that are unable to communicate. Maybe they're physically isolated. If that's true, then we might expect difficulties in applying a universal notion of truth to their statements and corresponding limitations on the objectivity of facts. That's just what's going on in the situation of GHC with friends. Given her isolation, Alice can't communicate the outcome of her measurement to any of the others. There's no record of this outcome after Eugene's measurement. Essentially, Eugene's measurement wipes Alice's slate clean. And then the sentence A is no longer accessible at any context. On the other hand, the sentence A is accessible at Bob's and Charlie's isolated labs just after their measurements, even though they actually can't assess it. They can't assess it because they're space-like separated from it. Why is it accessible? It's accessible because the Born rule is applicable to predict triple joint probabilities of outcomes in all three labs. That's why it's okay. That's why it's accessible at Bob's and Charlie's isolated labs just after their measurements and just after Alice's measurement. Okay, so objectivity. I'm getting to the end here, so don't give up. Okay. Thomas Nagel wrote a famous book, a famously titled book, The View from Nowhere, in 1986. To express an ideal of objectivity according to which a statement expresses an objective truth, just in case its truth depends only on how things are in the world. It has nothing to do with any context in which it might be assessed as true or false. A statement that meets this ideal may be called transcendently objective. Well, what I think the paradox shows is that a sentence like A or U about the outcome of a quantum measurement can't be used to make a transcendently objective statement about the world. It can't be used to state what Chaslov called in his, I think, 2018 paper, a fact of the world. So I'm on board with that, Chaslov. Okay. It further shows that there's not even a perspective invariant fact about each outcome in GHC with friends. That's to say, a fact expressed by a sentence that's true when assessed from every context. Alice's sentence A is not accessible from Eugene's context. But since no sentence is true at one context of assessment but false at another, I think it's misleading to say that facts are relative in GHC with friends. It's not that the facts are relative. What's relative here is factuality, whether something is even in a position to be called a fact. That's what's in question. Okay. All right. That's why we don't have analytic truth relativism. We have something weirder in a way, but more friendly to the objectivity of science. Okay, finally, why don't scientists or the rest of us have to worry about this failure of a transcendent objectivity? Well, basically, it's impossible physically to isolate labs so as to realize the Gedankenexperiment I just described. And measurements by Eugene, Daniel, and what's the other one? I forget. Cannot be performed. Johnny. Now, the universality of quantum theory allows GHC with friends as a Gedankenexperiment. That's fine, it's consistent with it. But I claim the experiment will never be performed, realizing it would require an impossible combination of the absence of decoherence external to each laboratory with the presence of just the right kind of decoherence of apparatus and recording states within that laboratory to permit the extraordinarily complex interactions needed to implement the X-type measurements using delicate correlations like UVW equals -1 that led to the paradox. Now, I'll claim even more boldly, this is not just an impossible combination for human scientists to create. It's beyond the powers of any system complex enough to constitute an agent capable of performing a quantum measurement as a subsystem of a lab system. So if these bold claims are correct, then GHC will never actually have such friends. And that's a point about the physical world, but it's not a point about quantum theory. So let's call a statement imminently objective if it expresses a truth in all actual contexts of assessment. Well, first of all, the measurement outcomes in GHC with friends would not be even imminently objective. There are contexts in which some of those sentences don't express a truth. But the thought experiment will never be performed because quantum decoherence is pervasive in the only environment actually shared by all agents. This provides the only actual context of assessment for statements about the outcomes of quantum measurements. So these are all imminently objective. Okay. Again, going even more broadly, this all applies much more widely. Most, if not all, statements about the physical world may be recast as statements about the values of magnitudes. We're not just talking about statements about describing the outcome of quantum measurements. These include not only statements about setting of switches and knobs on experimental equipment and currents and coils, to quote a couple of John Bell's examples of beables, but also statements about the behavior of a mouse, the height of a plant, the structure of an fMRI image, and even where things are in and outside the lab. If I'm right, for one who accepts quantum theory, all such statements are just as objective as science needs them to be, because they're all imminently objective, even though no statement about the value of a magnitude is transcendently objective. So let me just sum up. Measurement outcomes provide data for a physical theory. Unless they are objective, they support no objective scientific knowledge. This is my anti-cubism rant, if you like. So the outcome of a quantum measurement must be an objective physical fact. But recent arguments purport to show that if quantum theory is universally applicable, then there's no such fact. This calls for a reappraisal of the notions of truth, fact, and objectivity. If quantum theory is universally applicable, truths about the physical world include a fact about each quantum measurement outcome. These physical facts lack an ideal kind of objectivity, but a more modest objectivity is all that science needs. So science can continue to produce objective knowledge, you'll be relieved to hear. Okay, so I have a couple of slides where I give you references here, and I will simply repeat the first reference slide with these recent papers. And I'm happy to put this up again later if people want me to. And here's some background material of a more general kind. Thank you.
Thank you very much, Professor Healey. So you can hear virtually everyone applauding. I know it's not very easy to upload online. First of all, I will let Johannes Frankhauser ask you a couple of questions, and then the discussion will be open to everyone, and everyone will be welcome to make comments and discuss. Johannes?
Yeah, sure. Well, I happily accepted to initiate the discussion with one or two questions. And thank you very much, Richard, for this interesting talk. I found it really intriguing and thought-provoking. Perhaps I would want to go back to some of the technical aspects that I was a bit puzzled by. I guess my first question is, and these things appear at the very beginning of your talk where you present the experiment, the thought experiment. Yes. So I think that the first question I have is, how do we really distinguish between your assumption of single outcomes, or in the Cavalcanti paper, what's called the absoluteness of observed facts or observed events, and the assignment of a hidden variable, for example, the existence of a hidden variable that has an actual state. Of course, I think your assumption is not really the same as a hidden variable assignment because it's slightly weaker. It could be that the absoluteness of observed fact is just saying that there's an actual outcome, but it could be more than one. So it doesn't say that there's a single actual state. I think you do that though with saying.
Oh yes, it is very important that this is not a many worlds view. This is a single world view, and there is a single outcome.
Sure, right. So my question, I think, is how to define what an observed event is, and I guess I'm asking this because unless we believe there is really a something like a Heisenberg cut, where we distinguish between a macroscopic observer and a microscopic observer, or just a microscopic interaction with a very small system and a macroscopic system like an actual observer. Unless we believe that, I don't think there is really a difference in just using the thought experiments with or without Alice, Bob, and Charlie, because they basically would just copy the hidden variable if it existed. So I guess that's my first question. So if quantum mechanics really is universally valid and should apply to all scales, what is really different from assigning a hidden variable and assuming that there's a definite observed outcome?
Well, when people talk about hidden variables, there's some discussion about whether that phraseology is even appropriate. Some Bohmians, for example, think it's inappropriate because the supposedly hidden variables are the only things you see. They're the positions of particles and so on. But I take it that the outcome of a quantum measurement is certainly not hidden. It's observable. That's what people record after making that observation in their labs. So there's nothing hidden about it. And there's no assumption in this argument that the outcome of a quantum measurement reveals the pre-existing value of the magnitude that was being measured. That's an assumption in the GHZ part of the argument, which was ditched by the time we got to the GHZ with friends argument. So I don't see there's any temptation to think of the single outcome of a quantum measurement as a hidden variable. Perhaps I didn't appreciate your reasons for thinking that it might be.
Yeah, so I think maybe one comment on that, and then I've got another question. I think as soon as you state something, and you do more emphasize this more in your archive paper also, as soon as you have the Wigner's friend scenario where you have a super observer that thinks that ascribes a superposed state to the internal observer, Wigner, but at the same time you want to assume that Wigner himself observes a definite outcome. As soon as you have that, that's assuming that there's an actual state that Wigner's friend assigns to the system, and it might be just two Wigners, of course. Two Wigner friends, of course, but still, in all of the theories we have so far, many worlds in the Bohm theory and hidden variable theories in general, and QISS as well, you don't have to buy into the argument that the wave function is just a bookkeeping device if to get to the conclusion that you can have internal actual states, but still external observers that describe the system in a superposed state, that describe the observer to be in a superposition. So I don't really understand where the cut is really.
There is no cut. There's part of my view which was not highlighted in this presentation, according to which the meaning of a magnitude claim, like the spin is up in the z direction, is dependent on inferential relations that hold between that claim and a bunch of other claims. And if those inferential links are very weak, then the claim doesn't have much of a meaning at all. There's a kind of continuum of meaningfulness in a magnitude claim, which matches a corresponding continuum of decoherence in a model of the situation. And when you have a very high degree of decoherence in a particular basis, then claims about the value of a magnitude, which is, as it were, diagonal in that basis, have a very rich meaning and deserve to be thought of as true or false. Decoherence is only approximate, even though it's very good and can be very robust and very rapid. So there is no limit to meaningfulness, as it were. And there is no need to have a cut anywhere. Claims about the z-spin of a silver atom after it's passed through a Stern-Gerlach magnet oriented in the z direction are very lacking in meaning and should not be considered to be true or false because they are not sufficiently significant. But claims about the position of a particle which has detected a silver atom on a screen, those statements have a high degree of meaningfulness, and therefore we are warranted in taking them to be true or false. And the high degree of meaningfulness correlates with the high degree of robust positional decoherence in that context. So that's an additional part of my view that did not come out in this presentation. I'm going into it further in response to your question because it makes it clear that I neither want to nor need to talk about cuts. There is no microscopic, macroscopic divide.
Okay, thanks. That was helpful. I guess I'll want to come back to this later. So another question I have is concerned with locality. I was very surprised that you claim you don't need this assumption in your thought experiment, or let's say the weak assumption of contextuality in the sense of Koch and Specker, let's say. And I was surprised by that because if we want to try to run, let's say again, in a hidden variable model, what the thought experiment looks like, then you can get a situation where you have the super observers, which you call Eugene, Johnny, and Daniel, I think, and then you have Alice, Bob, and Charlie. And after Alice and Bob and Charlie perform the measurement, and then the super observers perform a measurement, it could well be that the states of Alice and Bob and Charlie, they just change a posteriori. So that would give rise to some non-locality or non-contextuality, and then we wouldn't have to draw the inference that there is no scientific objectivity. Of course, what changes for Alice and Bob and Charlie is not only that the spin state will change, but obviously also the whole memory state of Alice and Bob.
Yes.
So I think
so true.
Yeah. So I think we should have an assumption of contextuality or locality here.
No, I don't understand how that's relevant. I agree with you that after the measurements of Eugene, Daniel, and Johnny, the states of the three labs on which they're performing measurements will be radically different. I said at one point that Alice's record would have been completely erased by the measurement on her lab by Eugene. So those things change for sure. But what's relevant is what they were before, not what they are afterwards. The argument to derive the almost contradiction concerns what Alice's measurement outcome was before it was erased.
Mm-hmm. Okay.
Well, thank you, Johannes, for your questions. And I would suggest now that we open the discussion to everyone. So first of all, Professor Healey, if you don't need your slides anymore, I would suggest that you stop sharing them so that everyone can see the face of everyone speaking. Thank you. And so now, if you have questions, then you can raise your hand, or you can ask questions directly in the chat, or unmute yourself and ask them. There are already few people who have asked to make comments and ask questions. So first there will be Alexei Greenbaum, then Czeslaw Bruckner, then Carlo Rovelli, and Andrea, and we'll see. So Alexei, if you want to ask your question first, go ahead.
Merci, Pierre. Thank you. Thanks very much, Richard. I much appreciated this attempt at putting together Wigner's friend argument and contextuality, and I think there's a lot to be learned from this marriage. So let me first tell you what I think the main lesson is, and then tell you why it doesn't work. For me, the first question I had, and sort of the main lesson for me personally, is the following one. Many people are talking right now and have been talking for a while about experiments of Wigner's type, of Wigner's friend type, in which an observer, say Alice, will not disclose her measurement result, but there will be some thermodynamic signature of the fact that she had done her measurement. So just some signature, I've done a measurement without disclosing the result. What this marriage with contextuality reveals to us is that mere information about the existence of a definite measurement result for Alice may lead to contextuality paradoxes. So even if there is just a thermodynamic signature of the measurement being done, without any result or anything, we don't know about that. That alone will suffice for a paradox. And then I will agree with your analysis about, the sentences. Of course, this reminds us very much about Niels Bohr's insistence on language and communicability and things like this. But I think that this is pushing us a bit further than Časlav did in his nature physics opinion piece, because this pushes us in the direction of saying that not only facts in terms of states of quantum systems are relative, but the very identification of quantum systems is relative. So the way to get out of that Cohen-Specker paradox or Mermin paradox, whatever you call it, is to say that the very identification of systems is relative. So it's impossible to multiply values that pertain to this photon, because this photon is a relative notion. So Alice identifies a system for her, and Eugene or whoever identifies a different quantum system. You cannot say this is the same quantum system, let's multiply these values. So in order to get rid of that paradox, you need to go a bit further and say that not only facts are relative, but identifications of systems as theoretical entities are also relative.
This sounds very interesting to me. I would really like to learn from you the source of the papers you're referring to, so I can see what they're doing and how it relates to what I've been doing. So this is just a good question for you now, to email me the references. I can follow up on it.
I'll do that.
Thank you.
Yeah. Can I continue?
So yeah, if you don't have any more comments on that, then Časlav, you can go ahead. Yeah.
Okay, thanks, Richard. I really enjoyed a lot, and I think to a large extent I agree with what you said. Still, I have two comments or questions. One is more of technical nature, the other more of conceptual. The technical one is, you said that in this argument you do not involve locality issues and also not free choice. And if I could follow this correctly, there are in at least one reference frame, there is this measurement of Alice and Bob and Cleve simultaneously, and in the same reference frame later on of the Eugene, John, and Daniel. Am I right? So they
let's see that there's in what I'm calling the lab frame. Alice, Bob, and Charlie make measurements simultaneously,
yes.
And later in the lab frame, Eugene,
exactly,
and Johnny make.
That's what I meant. So there is this lab frame. Of course, you combine the different frames and planes of simultaneity. Now, but in that frame and in any other frame, we see that these measurements are somehow set in advance. We know what will measure Alice, and we know what will Eugene measure, and so on.
Yes.
And so whenever we have, that's more a general statement, it's whenever we have a fixed measurement settings, as it is the case here, we exactly know in each frame when which measurement will be performed. Then I think that there is a local theory that would reproduce these results, simply because the hidden variable already knows which measurement will be when performed and can adjust already, even if
there is a hidden variable. Yes.
If there is a hidden variable. So in that sense, I understand that that there is no locality issue here, because of course there is no freedom of choice issue.
Yes.
Usually want that choices are not are within the light common. But since there is no choices, there is no locality issues. But also then there is no, in a sense, quantum mechanics, if I may now stretch to the maximum, because then there is nothing particular in the GZ correlations. They can be simulated by a classical theory. That's, I think, it's that I'm not sure. I mean, I have to look at the argument more closely,
yes.
but I see that a kind of, I wouldn't say loophole, but it's not kind of close the argument.
Right. I mean, there's two games one can be playing in this area. One can be playing the kind of game that John Bell was playing, come up with an abstract definition of a theory of local beables, and then place constraints on it. Or one can be just saying, I don't care about hidden variables or local beables. All I care about is what quantum theory picks in this situation. And I'm playing the second kind of game. So it may be that some local hidden variable theory could exploit the possible failures of locality to predict the results of these experiments. But that's of no particular concern to the argument, because the argument is only concerned with what quantum theory says about this situation.
I think there is a classical model, or even...
Well, that may be true too.
QISS.
That may be true too, but it doesn't matter, because all we care about is what quantum theory says.
No, but I'm wondering whether you can go then that far and discuss the relativity of facts even for the classical theory, because on the level of Gedankenexperiments, the results are the same. So should we start to think about that?
Right. Yeah, that's possible. Again, that seems like an interesting avenue for future exploration.
Okay, so then I have another, which is kind of, if I understand, it's about relativity, not of facts, as you said, but of factuability, about, if I understand it correctly, about conditions that are necessary to meet in order to talk about facts.
Yes.
And in a concrete example, we can think about Alice facts, but then these facts disappear to be replaced by Eugene facts, and therefore it's we can define the factuability for one or the other agent, but not at the same time. I don't know how to say, or not simultaneously.
Mm-hmm.
Now, when I think about Wigner's friend and Wigner, then sometimes before I started this sentence, I also want to say that I like this connection with the decoherence, that part of the main part of the defining conditions that are necessary for having facts is that there is a kind of redundant imprint of this fact in the environment for decoherence. But then in a Wigner's friend situation, this is put to an extreme. And in a sense that, and this is, I guess, a little bit of mismatch in our understanding, is that indeed there are imprinted, multiplied records of the observation of Alice in her environment. And at the same time, it seems to me that Eugene can take the entire environment of Alice and make an observation of that with respect to his larger, maybe more complex environment, such that in a sense, both the conditions for factuability are simultaneously met, but one with respect to Alice and the other to Eugene. They cannot be combined. That's something which I think these kinds of no-go theorems provide us, but they coexist in some sense. So I don't know what you think about that.
I'd like to see it described a little bit more concretely, but I'm open to the possibility that when one has described it more concretely, there could be a kind of nesting of contexts, such that within one context, there is a fact, and within a broader context, there is no such fact. That would be consistent with my picture of things. But I'd like to see it worked out in more detail to see whether there is actually any such case.
Okay. Thanks a lot. I'm done. Thanks.
Thank you. So maybe Carlo now, if you want to ask your question.
Yes, thank you, Pierre. I have two questions. Richard, first of all, thanks. I mean, this is wonderful. I rarely listen to a seminar with such attention to every single word like this one. I'm puzzled by the same questions. You know that there are many things in which we have similar direction of thinking.
Yes.
So I very much appreciate what you're doing. It's really wonderful. I have two separate questions.
Yes.
The first maybe is it's simpler, and maybe it's just not a big is my not clear understanding of something, and it sort of follows up Johannes on locality and Czaslaw on locality as well. And let me formulate the question in this way. Suppose I am a hardcore believer in Bohmian theory, in the which I'm not, but is usual to think. And suppose that for me, the facts are the position of the variables in Bohm theory. Those are the facts of the world. And then I raise my hand, I stop you at that slide. I say, wait a minute. You say that single outcome and universality of quantum mechanics are sufficient to go to a contradiction. And I, the Bohmian, say, no, wait a moment. My variables always have a single value.
Right.
And therefore, definitely there is single outcome. Are you telling me that in some sense, my Bohmian reading violate the universality in quantum mechanics in some sense?
That's a very good question.
I actually think the answer is yes, but I'm not sure at all, and I want to know what you think.
Yeah. Well, certainly, Bohmians don't want to give up on single outcomes. And since the only other assumption was universality of quantum theory, they'll have to give up on that. I guess that's my immediate answer to the question. I see no alternative for that. Yeah,
and I think that I find this fact very interesting. I mean, and in a sense, I've been thinking about Bohmian versions of this this kind of experiment, ideal experiment you have, and your versions, your account of the story allows us to zoom in. You see, there is a sense in which Bohm theory violates quantum mechanics, obviously. Think of the double slit experiment. The particle goes through one slit, no doubt. So it is there. But then you cannot use that. You cannot use the Born rule. Since it is there, I compute the probability. So it blocks you for using Born rule in some cases. Okay, so, but let me put this aside. This was just trying to clarify. Maybe we can both think about that and come to and let me come to the second question. It's actually vaguely related. And it also follows up something that Czaslaw was saying. How do I put it? Andrea Di Biagio, who's speaking just after me, and me, we wrote a paper recently. The title is Relative Fact and Stable Facts.
Yes.
And maybe I'm oversimplifying it, but I think the stable facts are very much what you want to call facts now, in what you're supposing namely, if there is decoherence, sufficient decoherence, then we can restrict what relational quantum mechanics you can think about all the possible facts. And if we do, then we get the kind of stability that, as we call it, it's just a definition, which is the one that you say, well, if we just restrict to the facts, to what we call stable fact. And I didn't get the exact question, word that you use. I mean, the fact that comes when you have a sufficiently decoherent context where then we save, we understand what's going on. And in a sense, look, if we don't think about the philosophy, if we don't think about the deep issues, we know that that's the answer that explained very clearly what happened in the laboratory. And every time we actually say I've measured that, it is a decoherence situation when we say. So it, not in the ideal experiment, in the real experiments, we know what's going on all the time, and there is decoherence. And so we are in this context. And then I have two questions, if this is the case. One, I don't hope an answer. We're really happy to found our entire understanding of the interpretation of quantum theory, the fact of the world, on a limit, because in a sense the coherence is always always approximate.
Right.
That's it's not an objection. Is that do we really need to do that, or we do something better? And the second question is related to what Czeslaw is saying, and that I have no idea. I mean, Czeslaw may enlighten me or all of us. Is that could we figure out? It seemed to me that Czeslaw was saying yes. Could we figure out a situation in which we really have two decoherent, stable facts, which still are cannot be considered absolute, cannot be considered real fact, because if we took them for good, we would get contradiction in quantum mechanics.
Right.
I mean, can one engineering that or not? Or decoherence is it's sort of, there is a unique decoherence world once things start interacting with the other. I just throw that there as an open question. Czeslaw seemed to have some ideas about that.
Well, see, your first question is very interesting. I mean, from a long time ago, I've always felt that decoherence is never going to give you sharp facts. It's going to give you things which are good enough to be considered facts. And for a certain sort of philosophical perspective, that's not good enough. But I was actually using that as a reason not to take that philosophical perspective, to say that our language is the bearer of any claims about facts, and our language itself is not sharp enough, as it were. The world doesn't have the right language, and that we're trying to speak, as it were. The world is as it is, and we form languages to try to capture as much of our understanding of the world as we can. And when we use these languages, we sort of picture to ourselves that we are talking the right language to correspond exactly to the way the world is, but that's really an illusion. We're pushing language as hard as we can, and in this context, it's not like we've missed what's really going on. We've done the best we can using the best language we've developed, and that language fits pretty well as long as we don't push it so far as to believe that there's an exact correspondence between our language and the way that world really is. That was not very well expressed, but I'm not worried by the fuzziness of decoherence. I think it's good that we acknowledge it, because it illustrates a kind of limit to our attempts to describe the world. So that was the first question. Second question, again, I can certainly describe to my own satisfaction situations, very idealized situations, perhaps in a world other than the one we find ourselves, but still a world in which quantum theory is right, such that there are contexts in which there are facts relative to one context, but not relative to another context.
Right.
That certainly is a picture that I find quite attractive. But I then want to say that given the actual interactions that occur in our world, we are not going to encounter such cases. So that's why we have all the objectivity we need in our world. And had the world been different but still quantum mechanical, as it were, we would not be able to arrive at the kind of objectivity we can arrive at in our world.
Thanks. Yeah, I wouldn't disagree with anything you say.
Oh,
maybe Czeslaw want to make, I don't know if you have any.
No, I don't have anything to add, but I feel that we can, even in the, going back to what Richard said, even going into this limit, which is obviously a limit, it's not an absolute thing. It's a like we go towards cases where we have a relatively strong decoherence that allows us to talk about facts that even in that limit, the Wigner's friend type of experiment tell us that we can have situations in which there is sufficient evidence, both for Alice and from Eugene, each individually, to claim objectivity of their facts. And then there is this also Deutsch experiment that it's not really crucial for this type of argument, but if you say I don't want to believe in I don't want to rely on the formalism, decoherence, but only on kind of immediate interaction, communication between the parties, then Eugene can receive a message from Alice, in which Alice tells him, look, I do see a fact. I mean, I have all the elements of objectivity. Of course, she is not allowed to tell him the outcome of the measurement, but this, even if I don't know anything about quantum mechanics, this will be for me an evidence that I should start to think about coexistence of the facts of Alice and myself, which, of course, if you pursue this further, in the extreme case, would run into the difficulties of all these different no-go theorems. Yeah, so that's all what I would say. Yeah.
Last comment, Richard. Just to zoom in on what you think, because I understand that you're saying, and here loud and clear, there is a sense in which we can recover a solid notion of facts on which what we call objectivity is based.
yes.
And do science on that.
Right.
But that doesn't contradict the observations and the points that Czeslaw and others are making, saying sort of, yes, fine, but it's a weak one.
Yes, yes.
And if we want a stronger one, we can't, and we're obliged to a more relational notion of fact itself.
Right.
Which, by the way, is one that you yourself have worked on for long.
Mm-hmm. Yeah, no, I think that's right. We can get all we need to, but we've learned an interesting philosophical lesson, I think. That's my take on the situation.
Oh, I see. So your point is more a philosophy of science. Well, what do we mean when we're talking about facts? Careful. That's your core message.
Well, it's something that puzzled me when I started thinking about this. My disagreement with cubists was always regarding their willingness to go subjective on everything, to go subjective on probabilities, to go subjective on quantum states, to go subjective even on outcomes of quantum measurements. I thought that was a dangerous route to take, because in science we do want to reach agreement. We want to think that there's an authoritative answer to things that we can all agree on. That there is a kind of objectivity that is underlying our whole enterprise. So I wanted to rescue that kind of objectivity while still acknowledging that it wasn't the kind of ideal objectivity that some metaphysicians and other philosophers thought was essential or to be right.
Thank you. Thank you very much.
Thank you. Andrea, if you want to proceed.
Thank you. Thank you, Professor Healey. I think it was extremely interesting talk, and also I think this specific thought experiment you presented is very clear to understand, to think about this relativity of facts. And I wanted to say something similar to what Czeslaw and Carlos said, so I won't go back into that, but I would like also to maybe understand better your last point about this philosophical lesson, because my first reaction encountering this no-go theorems was, well, this experiment is actually impossible in practice, so we don't really care about this setup. Yes. But perhaps this is something similar that somebody might have thought 100 years ago when Einstein started understanding the relativity of simultaneity, and we would have thought, oh, we'll never go as fast as light, so we don't really care that yes. Simultaneity can be relative. And when developing technologies, actually, we need this understanding of relativity of simultaneity, even for GPS, for example. So my question is, perhaps humans will never be into this Wigner friend setup, but perhaps some intelligent agent inside a quantum computer might be in such a setup. Right. And perhaps those kind of agents will take center stage in our development of science as well. And so wouldn't we need a philosophical lesson for them as well?
That's an excellent question. I've begun to think about the implementation of the kind of Gedankenexperiment I described today. Since reading the paper by Bong and Cavalcanti and Wiseman, where they suggest that even though the particular experiment that they actually performed in the context of their work falls far short of the real thing, because almost everyone would agree that what they considered to be the friend was not really an observer in the experiment that they performed. Nevertheless, one could imagine doing a really fancy experiment with a quantum computer running in a strong AI program inside a lab, and that would perhaps count as an agent and perhaps count as making an observation within that lab. So I started to think about that. And my first reaction was, no, that's not going to work, because quantum computers have to behave coherently. And there has to be decoherence for there to be an outcome of an experiment. But then I thought, well, that's not quite right, because if there were a coherently operating quantum computer, which at the end of the day did implement some decoherent process and thereby actually record a result inside the sealed lab, then wouldn't that be enough? And I think the answer to that is yes, it would. But then the experiment, at least the one of Cavalcanti and Wiseman, involved having coherent control over the entire lab, reversing the whole process, essentially. So that would require the combination of decoherence in the lab and coherent control over the entire lab. And that is going to be incredibly difficult. I don't say it's totally impossible, but if that were to happen, then I would take it seriously. Even if that were to be possible, there's an issue about whether we scientists would include that quantum computer within our epistemic community. Is it in part of the game that we're playing as scientists? That's a further interesting issue that would have to be faced, but we're very far from having to face it today.
Right. Thanks.
Thank you. Now it's the turn of Marko Vojinovic, if you want to ask your question.
No, actually I don't, because Andrea has already asked the same question, so I have nothing to add.
Okay, all right. So Nick Huguet.
Hi, Richard. Thanks, that was really interesting. So I should say it's the first time I've come across that GHZ Wigner argument, so I don't think I certainly can't reproduce the whole argument, so I'm sure there are parts I don't understand yet. This was sort of in response to Carlos' first question about de Broglie-Bohm theory.
Yeah.
And as I understood it, there was an assumption in your argument as well that we have relativity of simultaneity. I mean, because we have those different hyperplanes that you're drawing in there. And it seems to me that's what's violated in Bohm's theory. I mean, because we have action, you know, instantaneous wave function collapse. And so that's what I was going to say as a way of sort of addressing what's going on there. I see Carlos shaking his head, but I also wanted to point out to a comment in the chat from Johannes, which also seems kind of relevant here. I'll just read it, right? It says, in de Broglie-Bohm, only the universal wave function can be used for coherent predictions. And that's then the kind of level at which I was thinking of things. However, for all practical purposes, there exists an effective wave function. And that's quite right, of course, that coincides with the quantum wave function that we standardly assign. In a sense, this can be seen as a violation of universality of QM, since some observers won't know the universal wave function, but it still may have an effect on their outcomes. So I think I saw Carlo nodding for a bit there, that if you're thinking at the level of the effective wave function, if that's all you're dealing with, then you are going to have this breakdown of universality, and I guess, and I was thinking in terms of the universal wave function. Does that help with that question a little bit?
Nick, can I just add one sentence?
Helps me.
For the effective wave function in the Broglie-Bohm to work and not to give wrong, you need the coherence. So it's exactly as you're saying. There is a violation of quantum mechanics in some sense if you use the effective wave function and you're not in a decoherence environment.
Okay.
Thanks, Nick. That clarified things for me.
There was otherwise another question in the chat, which has been asked by Renato Kierenberger. I don't know if I pronounced correctly, but if you are willing to ask your question yourself.
Thank you. Yes, the question is Wolfgang Pauli's explanation about measurements of A and B that we have to consider two systems that are composed of one still valued with his argument that one must differentiate between two layers of reality.
Two layers of reality. I'm not sure I understand that.
He says we have to take like a capital R that contains all the information that can be obtained from measurements on one, and one deducible from capital R, small r, which only contains the information which can be obtained by measurement one alone. So a complete description would have to assign characteristics of the state of particle one, which must already contain those of the properties of one, which accordingly to possible measurements of two, which do not interfere with one, can be predicted with certainty. So this was Pauli, Wolfgang Pauli, and I wonder if you can compose then your two facts in this framework. Or is
the only facts I was concerned with here, I think, were facts about the outcomes of measurements. I suppose there have to be also facts about the performance of those measurements. And there have to be facts about how to apply quantum theory in this scenario. So there has to be a fact about the assignment of the initial GHZ state, at least relative to some appropriate physical situation, if all quantum state assignments are relative to a physical situation, as I believe they are. I'm not sure I see a natural place to insert questions about facts about systems and facts about subsystems in the way that Pauli was apparently suggesting that one should do. I wasn't considering facts about, say, the combined triple of spin half atoms in this scenario. I was only considering measuring about the outcomes of measurements on a system which was assigned the GHZ state. So I don't see a clear way of connecting what you described as Pauli's thoughts with my Gedankenexperiment yet. But it's something I could think about. Could you give me a reference to where I can find Pauli saying these things?
Yes, it's in the correspondences, in the letters from Karl Mayen.
Yeah.
Maybe I can send it to you.
Is there a more specific reference, or is it easy to find in that correspondence?
It's 500 pages book. I will send you the letter. I
really appreciate it.
I think it's
Thank you.
406. A letter from 1935.
Yeah.
Thank you.
Thank you. Does anyone have additional comments? I see, Johannes, for instance, that you were making one in the chat.
Yeah, I think it has all been said already that I wanted to mention this in this comment, but I think that's a very important observation that in the Broad-Bone theory, you can only use the universal wave function to make a coherent prediction. So if you take the Renner-Frauchinger experiment that you mentioned in your talk also, things go wrong if you assume that quantum mechanics is universally valid if you just neglect the empty branches that exist in the Broad-Bone theory. So, for example, if you're one of these internal observers, the nested observer, and then Wigner performs an experiment on you, and you yourself, you just use one of the branches that you observe, you can get up with all these non-decoherent measurements that make the branches rebranch, and of course, then everything for your observation will change as well. So I think that's one sense in which we can say your second assumption, that the universality of quantum mechanics is violated in these experiments.
Yeah, that's your critique of Frauchinger and Renner. It sounds similar to my criticism in the paper I referred you to, the 2018 paper. In particular, that the very first measurement that was performed in the Frauchinger and Renner setup seemed to assume that there was a collapse, essentially. And of course, there would be no collapse from the external perspective.
Yeah, I agree.
I worry about any view of quantum theory that helps itself to a universal wave function. This is one respect in which I am actually sympathetic to the views of the cubists who deny there is such a thing as a wave function of the universe, on the grounds that wave functions are only useful for predicting probabilities of interactions with something else, and there is nothing else if you're really talking about the universal wave function. So I'm suspicious of a view of quantum theory that requires, in order to be clearly stated, that there exists a universal wave function.
Alessandro Capurso, I see your hand is raised.
Yes, thanks. Thanks, Richard, again for your interesting presentation. I was wondering about the universality of results, how can be then causality affected, in the sense that from a quantum information perspective, usually logical consistency is at the base of then causality. But if we don't have universality of results, then by consequence also causality may be made at risk. And so my question is, in an emerging causality scenario, how this causality emerge actually if we don't have universality of results? If there is the thermal action we were referring before, that may cause event. And if the event is related to the thermal action, then I would say that in this case, this could be then a posteriori considered a universal result. So I was trying to figure out the link with the loss of causality due to the unavailability of universal result and the thermal connection with possible events that then are a posteriori universal.
Could you tell me what you have in mind when you talk about causality? I always have trouble understanding that word.
Causality in a sense, of events that are logically needed for the following one. So events that affect the other in a causal way, in a general sense, basically.
Okay.
It could be said that causality could emerge from a kind also of a logical consistency, in the sense that the logical consistency is a weaker requirement than causality.
Right.
But logical consistency requires some kinds of universality of result, or at least the concept of information that should not be contradictory or overdetermined.
Right. I'm still not sure I understand what you're saying. I'll try and address what you're saying with incomplete understanding. I do think that it's interesting to ask about what I call causation in the context of quantum theory. I mean, obviously, the issue of causal relations looms large, understanding violation of Bell inequalities. There are philosophers and I think some physicists who think that the kind of non-locality that's manifested in experimental violations of Bell inequality shows that there is such a thing as instantaneous action at a distance. And there are other people who think, well, no, there's some kind of causal relation between, say, the preparation of the pairs involved in those experiments and the individual measurement results. So issues of causation sort of loom large in that context. And in that context, I do think that the view of quantum theory that I've been trying to develop has interesting things to say about what the causal relations are. And those interesting things emerge from a treatment of causal relations that appeals to the possibility of intervention on a candidate cause event to see whether that intervention might, as it were, have consequences for the candidate effect event. And I think if one thinks in interventionist terms, it becomes pretty clear what the causal relations are involved in violations of Bell inequalities, and that there is no instantaneous action at a distance involved there. But I apologize because what I've just said is probably totally irrelevant to what's really bugging you.
What you said is that actually there is causality from some perspective, while on the other hand, if there are no universality of results, it's hard.
Well, wait a minute. I mean, certainly I think one can describe, one can find a context in which one can talk about what the facts are in an experiment demonstrating violations of Bell inequalities. It's a context in which the outcome of the experiment on each wing of the experiment is a fact in that context. So factuality it doesn't raise a particular issue, I think, here. But once one has these facts in those contexts, then one can discuss causal relations between events that figure in this scenario. And there are interesting things to say. So I don't think that having facts somehow be less than what I call transcendent has any implications for how one talks about causality in the context of violations of Bell inequalities.
But how do you arrive at facts from events that a priori are non-universal?
A priori are non-universal. I'm not sure I understand.
In your speech, you say from this different perspective.
Yeah, I mean, there might be, one could try to cook up a Gedankenexperiment in which all the facts I've been talking about, describing outcomes of measurements involved in demonstrating violation of Bell inequalities, only count as facts relative to some context, whereas in some other context, they don't count as facts. One could try to cook up Gedankenexperiments of that kind. I mean, one could have the Bell violating experiments performed inside an isolated lab, and then take the perspective from outside the lab. One could do that. I'm not sure how interesting it would be, but one could do it.
But the way you define the context is actually a causal way. It's the environment, it's all the preparation that you have done before to set up the thing. So it's a macroscopic causal thing.
Okay, good. Now I think you're getting at something which is important to my view, that I help myself to things like an environment and to interactions which would be modeled by some decoherence process in quantum theory. And even in discussing the thought experiments of Wigner's friend, we have to talk about isolated laboratories. And what does isolated mean? It means that there are no external interactions which will interfere with what's going on inside the laboratory in such a way as to disrupt the processes that we're trying to talk about as occurring within that laboratory.
Of course, they might be isolated, but within the lab, someone is doing some causal choice to set up the environment.
Oh yeah, sure. I mean, we suppose that is what's happening. We suppose that when the friends enter their labs, they already remember what they're supposed to do, that they're supposed to perform these spin measurements or spin component measurements, and that they're supposed to set things up so that those are performed correctly. So we're assuming all of that, yeah, for sure.
Okay. Thanks. Maybe we can get it better also.
I hope I said something that helps to answer your questions. I'm not sure that I did.
Partially, I still have some doubts for how you arrive to the definition of fact from a condition of undefined or even not universal results. So basically, not logical consistent starting scenario is something that.
No, I'm trying to preserve logical consistency everywhere. That's a ground rule.
Okay, it's sort of in general speaking, in information theory, it's hard to have a word without logical consistency at the base.
Yeah, right. We're in agreement on that.
Thanks for your clarification.
Thank you. Francesca, you have a question.
Yeah. Hi, Richard. It's Francesca.
Hello.
I enjoyed a lot your presentation about Wigner experiments and so on. And then you had in the end this the main message of your talk about objectivity. And I wanted to disentangle a bit these two different things, because so I would like to understand better which kind of notion of objectivity you are hinting to. And what I fail to achieve is to see how quantum mechanics is obliging us to look in this way, because it seems to me that the kind of objectivity you're hinting to, it's already present even at the classical level. You were giving nice examples of the way in which there are situations in which it's not even possible to arbitrate in which context a property has to be evaluated. And your examples were completely classical. So my question is, then Andrea was saying, okay, maybe this is relevant for a possible intelligence that use quantum mechanics, but yeah. It seems to me that in fact what we are discovering from quantum mechanics is that even at the classical level, the notion of objectivity such as the transcendental one are completely unattainable. They are fantasy of the 20th century, and we have to use in a very broad way this weaker notion of objectivity.
Could you elaborate on cases in which what I call transcendent objectivity is not sustainable? In other contexts, I'm not sure I understand that yet.
Well, you were mentioning transcendent objectivity, and my understanding was that you were saying that there are situations in which it's not possible to have a true fact in every context of assessment. This, have I misunderstood?
Right. I think we are presented with such a case in the Wigner's Gedankenexperiments. Yes.
Yes. But so my point is that we don't have to confine this finding about objectivity only to the case of to the quantum world, but it seems that this is something.
That's the only place I found it. Where else should I look?
Well, your example about time zones was very nice. You were saying that we cannot tell what is the time on the sun.
Yeah, but that one I think we can resolve. That, I mean, my take-home lesson from that example was that sometimes science can help us out and give us ways of assessing claims, which at first sight we might think could not be assessed. So that was, I think, we're a success story where we can bring, in this case, physics to our aid to show how we can assess claims for truth or falsity, even though at first sight we seem to be unable to do that.
Yeah, but that's very good. That's very good. So we have to bring more information in somehow.
Yeah, right.
To do that. Right. So my what I fail to understand is how this is different in quantum mechanics, as it is always the case when we consider this kind of fact of the worlds. So in quantum mechanics, very well, we have to bring the context in. We need to tell with respect to which observer effect is true. So why do we have to differentiate one level with respect to the other? What is different? Isn't the same kind of objectivity in the classical world and in the quantum world to be applied?
Okay. In the case of what time is it on the sun, we can tell a story, a single story about what's happening in the physical world. And what the spatiotemporal structures are in the physical world, such that on the basis of that story, we can defend the claim that there is a non-relative fact about what the time it is on the sun, okay? Given all of the assumptions we've built in, perhaps it's arbitrary to select a particular time zone for the sun. Perhaps it's arbitrary to pick out a particular frame which determines simultaneity between the Earth and the sun. But once we've made those choices, then there is a fact about what time it is on the sun. So here we've nailed something down and we end up with an objective fact. In the case of the Gödel universe, that we can't do that because physics there tells us there's just no way of assessing the statement about what time it is somewhere else in the Gödel universe, because there is nothing we can appeal to analogous to what we did appeal to in the case of what time it is on the sun. And in the case of quantum theory, I take that to be like the Gödel universe example, where our most fundamental theory lacks the resources to enable us to say what the facts are in some other isolated decoherence environment.
Yeah, but again, very good. But you're making my point that what we have learned about the quantum world applied also in a more general context. It's not specific of quantum mechanics. Well, more general about.
It's not specific to quantum mechanics in the sense that there's a very general issue that arises in all of these cases, and it's a similar or even the same issue. But only in the case of quantum mechanics can we not resolve that issue, at least to my satisfaction, by appealing to a unique objective description of the world. We can't do that in the case of quantum mechanics because all we get is facts in these different contexts, and there is no fact external to all of these contexts to which we can appeal.
But I fail to see how in the classical world there is a way to appeal to a universal objective.
Well, we're appealing to the structure of space-time, whether it's Newtonian or relativistic, and using that notion, that structure of space-time to pin down what we mean by talking about same time as at different locations, and to further, perhaps by arbitrary convention, just select a particular time zone and then say, okay, now we've made those choices. Now we know what it means to say, to ask the question, what time is it on the sun right now? We can do it. And we can't in quantum theory. We can't jump out of one context and land in another context because the contexts are sufficiently sort of isolated from one another. We can't enlarge the context, put it that way, right? There's the context of us here on Earth. There's the context of the sun. Is there a bigger context in which we can locate both of them such that we can pin down the question of what it means to say and how we decide whether it's true to say what time it is on the sun right now? And the answer there is yes, we can enlarge the context to a global context. We can't do that in quantum theory, at least if what I've been saying is right. There's no enlarged context which includes Alice's measurement result and Eugene's measurement result. There's no such thing. So that's the difference, at least the way I see it. Does that help?
It clarifies, but at this point I want to think more about this.
Okay, good. Me too.
So thank you.
Can I make a comment?
Any other comments? Yeah.
Okay, so I'll try to be quick. Richard, thank you first of all for this very nice talk. I mean, I'm not following the details of everything, so it might be naive, my question, but trying to sharpen, I don't quite understand, sounds interesting, but I don't quite understand this idea of having different factualities. So my factualities.
Yes.
It was the term you used. So I understand that this is not a relative fact in the sense that there is a context in which something is true and a context in which something is not true. Like if I wear green glasses, the wall may be green or white. This is not that kind of relativity. You're saying that there is a set of facts that are somehow simultaneously true, and then there is another set of facts that are also consistent and simultaneously true, but these do not agree. And there can be many of those. So my question is this. You are saying that in practice, nobody's going to be able to do these measurements, but this is just a question of technological power. So in principle, I can assume somebody that does this. And my question is this, just to sharpen, what is the implications? If somebody, let me assume some super powerful agent that can take a laboratory and do a quantum measurement on it. What if he just finds one set of those facts? So
he
does the measurements and he finds only one set of those truth or false values. Right. But we don't know what reality is. You know. So let me just assume. What does he conclude?
Well, he concludes that this was the outcome of the measurement, of my measurement.
Does he conclude that quantum mechanics is wrong?
No, not at all. I mean, the whole discussion of the thought experiment was set within the context of quantum theory. I was using quantum theory to structure the discussion by saying what the Born rule predicted for the outcomes of joint measurements in that scenario. So this was all using quantum theory.
But so statistics has absolutely no role in this if he does. So
statistics only play a role in that.
What I'm asking is that even if you did have the power, excuse me, even if you did have the power to do these measurements, is there any way to know whether?
Well, just think what would happen. I mean, if all of the measurements I described could be performed, then after it's all over, the only outcomes which would be recorded would be the outcomes of 3 measurements. The measurements by Eugene, Johnny, and Daniel. The outcomes of the measurements by Alice, Bob, and Charles would have been erased, and there would be nowhere to look for a record of those measurements. So if this were all done, all you'd have left at the end of the day would be the records of 3 measurements, which makes it a rather peculiar experiment to perform. Because how do you know you've really performed it if half of the measurement results have been erased during the course of the experiment?
I see. Yeah. Okay. Have to think about this. Thank you.
I hope that helps.
Thank you. If there are no other comments, then I would suggest that we close now, because it's already 2 hours that we are discussing. So I would like to thank you again, Professor Healey, for this time. And I would like also to thank everyone for the nice discussion that followed.
Yeah, thank you all. And if anyone would like to follow up by sending me emails, I did request further information of a number of you saying interesting things. I would really welcome that. Thank you very much.
Thank you. And I announced the next QISS seminar, which will be on January the 28th, and it will be Lee Smolin talking. That's all for today. Have a good day and see you soon.
Bye.